Welcome to our example 1 for Bernoulli first order differential equation. So before I even go to example 1, let's come back to the right hand side of the screen. What is Bernoulli? So Bernoulli looks very similar to linear first order. So remember, the linear first order can be written as y prime plus some function of p times y, p as a function of x or a function of t, whatever the independent variable. So y prime plus py equal to q, where p is a function of t or a function of x, and q is a function of x. So that's linear. So this is linear. Bernoulli looks very similar, but it's not linear. So the Bernoulli first order differential equation is, if you can write a first order differential equation as y prime plus py equal to q times y to the power n. So that's Bernoulli. Of course, if n is equal, so we're going to assume that n is not equal to 0 or 1, because if n equal to 0 or 1, it will be linear. So we're going to avoid n equal to 0 and 1 for Bernoulli. And if it is Bernoulli, then the substitution that we are going to make is, again, is a special type of substitution. Is v equal to y to the power 1 minus n. So that's the main substitution. V equal to y to the power 1 minus n. And if you do the substitution, the Bernoulli will become, at the end of the day, linear or separable. So let's look at this example 1 on the left. So if you look at here, the coefficient of y prime better be 1. So I have to divide both sides by x. So let's rewrite. If I divide both sides by x, this x will vanish, and then I have y over x, which I rewrite this way, equal to 1 over x times y to the power negative 2. See, this 1 over y square I write as y to the power negative 2. And remember, I am dividing both sides by x, or you can think I'm multiplying both sides by 1 over x. And when you distribute that, you will end up with this. And you can see this is actually Bernoulli. In this example, p is equal to 1 over x, q is equal to 1 over x, and n is equal to negative 2. So I can write it down here. P is equal to 1 over x, q is equal to 1 over x, and n is equal to negative 2. Now, to solve Bernoulli is slightly longer than homogeneous and other examples that we saw, because the algebra is little bit involved. So you have to be patient. So let's do that actually. So the first step, you do the substitution v equal to y to the power 1 minus n. But our case, our n is actually negative 2. So let's do that. It's y to the power 1 minus negative 2. That's my n. So which is actually 1 plus 2, or y cubed. Let's take the derivative of both sides with respect to x. So dv dx is, remember, y is a function of x, so you are using chain rule. So you get 3y square, 3y square times dy dx. You have to take the derivative of y with respect to x. So we're using chain rule here. So let's solve for dy dx, because you want to solve in place of dy dx, right? So you need to know what is dy dx. So let's solve for dy dx. So I'm going to divide both sides by 3y squared. So dy dx, let me write that in the beginning, equal to, I'm dividing both sides by 3y squared. So 1 over 3y squared. Let me write this way. Okay, let me write 1 over 3y squared is fine. 1 over 3y squared dv dx. Excellent. So now in place of dy dx, I'm going to substitute this. So this goes in place of dy dx here. So let's do that. So I'm going to copy this here. So I start with dy dx, but my dy dx is this here down here. 1 over 3y squared times dv dx. And I'm going to copy everything else for a moment. Let's just copy everything else. So all I did, I replaced dy dx by my dy dx here, this one. In this differential equation, I have x, y, and v. Too much variable, too many variables. So your goal is to get rid of y. I should only have v and x. And hopefully it will be a linear equation in terms of v and x. So y should be completely gone. To do that, you always have to make the coefficient of dv dx 1. So I have to make this coefficient 1. How I do that? Well, to get rid of 1 over 3y squared, of course, you have to multiply both sides by 3y squared. So let's multiply both sides by 3y squared, because I want to make the coefficient of dv dx 1. So that's you should do here. So if I multiply out, so 3y squared times 1 over 3y squared is just 1. So I end up with only dv dx plus 3y squared times 1 over x. So that's just 3y, so I get 3. So let me just write, multiply y squared and y. So that will be y cubed. And 1 over x times 3 is just 3 over x. So this 3 and this 1 over x is just 3 over x. And y squared times y is y cubed. Equal to this side, y to the power negative 2 and y to the power 2. When I multiply, I get y to the power 0. Remember, you add the exponent, so you get y to the power 0, which is 1. So that's just 1. And 1 over x times 3 is just 3 over x. Now, y cube is actually equal to v. Remember here, go back. V is equal to y cube. So, because v is equal to y cube, I can replace this y cube by v. And once I do that, and I mean, that's a magic actually, or by a simple algebra, all this y vanish. Everything works out perfectly. So that's a very nice substitution that we make. V equal to y to the power 1 minus n. And if it is Bernoulli, this will always going to work out like this. All y should be completely gone now. So I'm only going to replace y cube by v. Let's do that. And this is indeed a linear differential equation in terms of v. So this is linear. And here v play the role of y. So v is the unknown function that we want to solve for now. So here, let's go back to the linear differential equation. So that's the p and that's the q. You can go back and watch my example on the linear first order differential equation. I believe I did 5 examples there, and watching them will really help you. So let's first find the integrating factor. So let's call it U. The integrating factor is e to the power integral of p dx. So that's the formula, and we derived this during that time. So it's e to the power integral of 3 over x dx. So that's just e to the power 3 ln of x, and that will give you e to the power ln of x cube, which end up with x cube. And here you can just take x to be bigger than 0. So let's just take x cube, and then we can just assume that the x is bigger than 0 here. So we just take one branches of the solution. So it's okay. We can drop the absolute value and then just take x cube. So let's assume x is bigger than 0. Otherwise, you have to divide into two parts. First solve when x is bigger than 0, and then solve x is less than 0, and end up with two branches of the solution. If you want, you can do that. But we're not going to be that formal for the moment. So again, what I'm saying here, just to make sure everybody understand, so this absolute value of x cube, you can divide into two parts, right? So that will be x cube if x is bigger than 0, and this will be negative x cube if x is less than 0. Because the cube is an odd exponent, we cannot really drop the absolute value as it is. So we have to be a little bit careful. So you go through the process for x cube if x is bigger than 0, and very similarly, if you go through the process when x is less than 0. In that time, the integrating factor is negative x cube. But we're only going to look at for the positive x, and you can do the other one if you want. So let's go over that. So if x is bigger than 0, so then I just only get x cube. So let's find out our v. Remember, v play the role of y. So from the linear first order, v is equal to something over something. On the top is the integral of u times q dx divided by u. In this case, the q is 3 over x. So don't forget that. So let's do that. So in place of u, I write x cube. Remember, when you find the integrating factor, you choose c to be 0. Do not add any c. But of course, when I find the general solution, I need to add c. So let's do that. So v equal to integral, the u is x cube and q is 3 over x dx over x cube. So this is just x squared. So all I have inside is the integral of 3x squared dx over x cube. Let's do the integral. So my v is equal to the integral of 3x squared is just x cube, because the derivative of x cube is 3x squared, right? Plus c. Very important to add c now. I can distribute, so I end up with 1 plus c over x cube. But don't forget, what is my v? Remember, v is equal to y cube. So I have to put that back at the end. So now I replace v by y cube. So I get y cube equal to 1 plus c over x cube. And that's my general implicit solution And then of course here the restriction is x is bigger than 0, so I should actually write that down. Not, don't forget that. Now what happens if x, if x is less than 0, then you replace x cubed by negative x cubed, the integrating factor, right? So in that case, I'm going to have a negative x cubed on the denominator, and I have a negative x cubed on the numerator. But those two negative actually going to cancel each other. Oh, look at the beauty here, right? So what happened? Actually, let's write it down. What happened if x is less than 0? In that case, your integrating factor is negative x cubed. In this case, what will be the v? Look at the v. V is going to be integral of u. In this case, my u is negative x cubed times q, which is 3 over x dx, divided by u. But look at the beauty here. And this negative I can bring outside, and that negative will cancel out with this negative. So you actually end up with exactly the same calculation as before. So actually nothing changes. So at the end of the day, the same answer is also true for x is less than 0. So this will be the answer for all x except x is equal to 0. Sorry, except x is not equal to 0. Excellent. And what is the solution? The graph of the solution looks like. Look at the GeoGebra, and let's put it here. So again, C, I use the slider for the C, and let's put our expression. So I get y cubed equal to 1 plus c over x cubed. I wonder what is the graph looks like. Beautiful graph. I really, amazed by this beautiful, beautiful graph. And of course, for each value of c, you get a solution. So at this point, my c is 2. When c is 2, you see that there are division of solution, or the branches of the solution here, right? Uh, at some point, it changes, right? Look at here, at some point it changes. And in fact, when c is equal to 0, you can see if c is 0, I get y cubed equal to 1, or y equal to 1. So that's my horizontal line. And if c is bigger than 0, I have this type of solution. So the one part decrease, actually the whole thing decrease. So this part is decreasing function, and this is also decreasing function. So the solution is always decreasing. And of course, the y-axis will be a vertical asymptote, because you can see it from the x cube in the denominator. What happens if c is negative? In that case, the function is always increasing. So c equal to 0 is like a critical value. When c is bigger than 0, the function is always decreasing. And when c is less than 0, the function is always increasing. And when I say function, of course, I meant branches of functions. So if you look at here carefully, so you have to be really careful here how it looks like. Anyway, we have a critical value c equal to 0. Perfect. Always remember, you can do it. Believe in yourself. Bye bye.